This video is for users creating their Task 1 CoSpace Auto Delivery program in Python. In this video, we will first create a simple Python program in the Development Panel GUI, and then learn how to upgrade the program to complete Task 1 using Python programming language. Let's begin. After opening your CoSpace Auto Delivery application, click on Compete Mode, and then the Open category. Select the challenge and then Python programming language. The Future City virtual environment will be launched. There are some basic CoSpace virtual environment features you should know before we start programming. To turn on the delivery system, click Displays in the top menu and then Delivery System from the drop-down. The distribution centers, collection stations, and navigation points and their IDs, along with the center line of the road, will be displayed on the virtual world. To adjust the viewpoint in the virtual environment, first, click anywhere in the 3D environment. Then use the QWASD keys to adjust the camera position. Pressing Shift together with the keys will make the movement faster. You can change where the camera is facing by holding down left-click and dragging your mouse. To reset the virtual environment to the home position, press Ctrl+H. To manually control the virtual robot, first click anywhere on the control panel, and then use the arrow keys to move the virtual robot manually. While the robot is moving, the live data information on the control panel will update based on the robot sensor's feedback. Based on the delivery task, we will now create a program for the robot to execute. Click on the AI button to open the AI development panel, which contains the AI programming interface. On the top of the interface, you'll find some file management buttons. To create a new project, click the New Project button. Give your project a team ID, team name, and project name. The default root directory for the project will be in your CoSpace Auto Delivery folder. You can choose to set up the directory in another location on your computer by clicking the file icon. Click OK once all the information is correct. Remember, once the team ID and team name are confirmed, they cannot be changed anymore. However, you can still change the project name if you wish. Each program statement is separated into two parts: conditions and actions. Conditions are inputs from the environment, and when they are met, the corresponding statement's actions will trigger outputs that control the robot. The program considers statement priority based on their order. The higher the statement, the higher the priority. Once a statement's condition is found to be true, subsequent conditions will not be evaluated, and the program will loop from top down again. Clicking on the info icons beside parameters will display their information tab, which explains what the parameters are used for, the variables utilized, and their value ranges or settings. There are also advanced conditions and actions where you can code in detail using the programming language you've chosen. Firstly, let's make a statement that makes the robot deliver packages successfully at collection stations. To create a new statement, click on the plus icon. Give the statement a meaningful name. We will name this statement Delivery. After the statement name is defined, we will add conditions to the statement. Set collection station ID to be between 0 and 15 and the distance range to be from -2 to 2. This means the robot will sense for every collection station, and once it is close enough to any one of them, the conditions will be met and the statement's actions will run. Next, we will define the actions to deliver the package successfully. Firstly, the LED must be blinking, so set LED status to flash. Secondly, the robot must stay still for at least 2 seconds, so set both wheel speed to 0 and duration to be 80 units, which equates to 2 seconds. Lastly, to make the robot leave the distribution center automatically after, we will utilize advanced action. First, increase duration to 100 units and then click the writing icon to edit the advanced action code. Now we can begin coding in Python. If duration is less than 20, which means the robot has stopped for at least 2 seconds, we will make the robot leave the collection station and turn off its LED by setting both wheel speed to 60 and LED to 0. For C users, this is the aforementioned code and C syntax. Next, let's make another statement called forward that makes the robot drive forward to reach the collection stations. We'll leave the conditions empty. Under actions, to make the robot drive straight forward, set both left and right wheel speed to the same value, 40. Once you've completed programming, it is very important to save and build your program. Save will save the most recent program that you've just completed. Build checks for syntax errors, create a Python source file for Python users in the program's root directory. Now you can click on the preview button to inspect the robot's behavior. Pressing the debug button will bring up the debug information tab that displays the variables and their values when the robot is running. In settings, you can choose which variables to display or hide by selecting or deselecting the boxes beside the variables. If we only want to monitor the current duration value, the closest collection station's ID, and its distance from the robot, we will only check the corresponding variables boxes. Press OK once you are done to apply the new settings. You can also click the robot button to display or hide the robot's information panel. Turn on the delivery system to get a better view of the stations. Once you are ready, press the play button to run the program. As you can see, the robot's information is being updated in real time on the information panels, and the robot is able to successfully deliver packages, scoring points. You can freeze the game by pressing the pause button. To resume the game, press the play button. If you wish to modify the program, click on the stop button to return to the AI development panel. Next, we want the robot to deliver to collection station, S1, right after the first delivery at S3. Using the delivery system, we can see that the robot will need to perform a right-angle left turn at navigation point P17 in order to reach S1. Step 1. We will create a new statement name turn P17. Step 2. Add conditions to the statement that only checks if the distance from navigation point 17 is between 0 to 2. Step 3, under Action, set duration to 100, left wheel speed to -30 and right wheel speed to 30 to perform a stationary left turn. To make the robot stop turning after it is facing S1, we will set an advanced condition. By manually driving the robot and using the information panel, we can see how direction changes with regards to where the robot is facing. Right is 90, bottom is 0, left is 270, and the top of the screen where the robot should be facing and heading after the turn on P17 is 180. Based on the analysis in advanced condition, we will write an if condition that checks if the robot's direction, rotation Z, is about to be facing the top of the screen, 160. And when the condition is met, the robot will stop turning and leave the navigation point by, setting both wheel speed to 60 and resetting the duration to 0. This is the aforementioned code in C as syntax. Remember, the robot considers the statements from the top down. So if the forward statement is above turn 17, the robot will not perform the turn when it reaches the navigation node and will continue executing the forward statement's actions as the forward statement doesn't have any conditions and will always be true. To change the order of statements, click on the statement you want to shift and use the arrow buttons to move it up or down. You can also delete statements by pressing the minus button. Now save and test the program. CoSpace Auto Delivery allows you to fully program the robot in Python programming language. Let's use the first program we created before, my first program, as an example. Open the project by selecting the program's SMP file. Click the Python icon. Your CoSpace program will be automatically converted into Python code. The Python code consists of variable definitions, system functions, and AI functions that you can modify. Let's look at the forward statement. If none of the above statement's conditions are met, set both wheel speeds to 40. The highlighted red segments on the right shows the interpretation of the forward statement in Python. We will modify this statement by changing both wheel speeds to 80. Now save the Python code as a new Python file. Name my first Python. Python files end with the file extension .py. We will now run the modified program by loading the newly created Python file, my first Python.py, in the control panel, and then press the play button. You will notice the change in speed when the robot runs forward. Now that you know how to create a basic auto delivery program using the GUI and have created and edited a Python file in the CoSpace template that can be used to program the robot in Python programming language, we will now go through ways to upgrade the program. For the load all task, the main objective for robots is to travel to and complete deliveries at all the stations as quickly as possible. The following are some viable strategies to achieve the objective, which we will go through how to implement in the subsequent sections of the video. Previously, to make the robot perform a turn, we had to manually set the duration, wheel speeds, and satisfactory condition with its follow-up actions, as shown in the code. However, if you look in the program's Python source file, you can find a pre-written function called turnTo that has two parameters. The first one is the starting angle, and the second one is the target angle. Once the angles are set and the function is called, the function will calculate them. Absolute difference between the angles, and then turn the robot towards the target angle by setting the wheel speeds to travel with the same value in opposite directions, before exiting the turn by setting both wheel speeds to move the robot forward once the angle is within the target's threshold. We'll now edit CureAction Case 2 P17 turns action to use the turn to function instead. After typing the turn to function, all you have to do is set the first parameter as rotation Z and the second parameter as your desired angle, 180 to turn up. We will standardize the direction of the turn action, and this will be coined as the turn up CureAction, instead of just turn P17. While we are here, we can also clean up P17 conditions by changing it to equals 17 instead of more than and equals and less than and equals to 17. We can also remove the turning duration as the turn to function will handle it. Now run the program to see if it works. Using the turn to function, you'll not only save time when programming your robot, but it also ensures smooth and controlled turning as the function gradually increases the turning speed with the angle differences. Finally, create 3 more CureAction cases, one for each of the remaining directions, down, left, and right with their corresponding directions, to fully standardize all the required turning actions. For the robot to deliver to all collection stations, it will first need to know how to travel to all the stations, and the simplest way to achieve this is through path planning. Path planning can be done manually by starting off with a digital map of the field, with all the station's locations. This can be done by moving the camera to the top of the screen and taking a screenshot, or sketching a diagram as shown. Then on the map, plot a route for the robot to follow that goes to every collection station. After that, you can list down all the nodes where the robot is required to perform an action in sequence and highlight parts where special actions are required, such as needing to perform U-turns or different turns at separate stages. Take into account the total distance and the amount of turns needed, as these will affect the total time taken to complete the path. After you have finished planning a path, manually add more turning condition statements for navigation nodes in the Python code, according to the path setting and naming them with the corresponding navigation node IDs. We will disregard the other conditions such as the station's turn activation distances and resulting actions for now. As for the U-turns after deliveries, instead of just immediately moving forward, the robot will instead first check if it's on any of the stations that require a U-turn in the CureAction delivery case. Since the U-turn on S10 causes the robot to face left and the U-turns on S11 and 8 causes the robots to face up, we will incorporate 2 separate checks to activate the different turns required. Set the actions to a random CureAction for now. And if the robot is not on any of the special collection stations, it will run forward like it used to. Once you are done with your program, you can also try other paths that give varying results and find one that's most suitable for your program, which provides the best results. With the foundations of the path set up, we can incorporate the other strategies that will be taught in the following sections to make the program complete task 1. The turn to function and turns we have programmed the robot to do previously are spin turns, where the robot rotates around its vertical axis without changing its position until it faces the correct direction by having both wheels drive at the same speed in opposite direction. However, there is a turning method called curve turn, where differential steering is used to execute smooth and gradual turns. Using curve turns to turn left or right is faster, as both wheels are constantly driving forward, not requiring the robot to stop, and it also cuts the corners of turns to reduce the travel distance. This is the sample code for a function that makes the robot perform a curve turn called curve to turn. It is similar to the turn to function, as it accepts 2 parameters, a starting angle and a target angle, where it will face after finishing the turn, implemented by pasting the whole function under the turn to function, and then replace the CureAction cases for turning to each of the 4 directions, to use curve to turn instead. However, since curve turns require space to turn, we will still use spin turns to perform the U-turns after deliveries, where the space is confined. According to the path, we made the robot needs to perform a U-turn to face left after delivering to S10 and face up after delivering to 11 and 8. Thus, we will create 2 more curation cases using the turn to function for the aforementioned directions. To make the robot move faster, we can also increase some of the speed values. To increase the spin turning speed, we can increase the minimum tuning speed to 20 and increase both wheel speeds for whenever the robot is set to travel forward upon the completion of an action which are in the turn to function and the delivery action, to 100 the maximum value. We can now set the turning actions for all the path conditions we set up earlier, according to the path, turning up using cure action 2 on P19, and so on. For the majority of minimum navigation distance to trigger the smooth turns, set them to at least 15, as smooth turns are required to start before reaching the navigation points, or else the robot will overshoot the turn and go off course. However, the turns at the corners of the road at P19, 4 and 14 will require the curve turn to be triggered later, so set their navigation distance to be below 5 instead. Don't forget to update the cure action cases for the U-turns after the deliveries, in the cure action delivery case, with the correct ones. Looking at the fully planned path, you will notice that the robot revisits stations, and with the current program, the robot will continue to deliver to collection stations even though they have already received packages, wasting time. To prevent the robot from unnecessarily stopping at collection stations, we can create a new self-defined variable called statuses that indicates to the robot whether to stop at collection stations or not. When status is 0, the robot will act as usual, delivering to collection stations whenever they are close enough. However, if status is toggled to 1, the robot will ignore collection stations and drive past them. To set up the status variable, first, define a new variable named status and initialize it with an integer value of 0, under where all the other CoSpace rescue variables are defined, at the top of the code. Next, in the game's 0 function, include status in the global statement to use it. We want status to be set to 1 before passing S2 again, after delivering to ES13, and reset to 0 after passing S2. To do this, we will create a new condition in the cure action delivery case that checks if the delivery station is 13, and if it's true, switch the value of status to 1 to reset the value of status back to 0 so that the robot can continue delivering to collection stations after passing S2. Go to the P17 turn action, where the robot will have just cleared S2, and reset the value of status to 0. Finally, to prevent the robot from delivering to collection stations when status isn't 0, go to the delivery conditions and add another condition that requires status to equal 0 before performing the delivery action. We can also utilize the newly created status variable to dictate which turn statement to execute for a given point on the path. For example, following the early sections of this path, the first time the robot passes navigation nodes P17 and 18, it shouldn't perform any turns, but on the second passover, the robot performs turns on them. Since the robot's status is set to 1 on the second passover to prevent repeating the delivery on S2, we can add a new condition to ensure the value of status is 1 before performing the turns on P17 and 18 as shown. For the other navigation nodes where the robot is required to perform different turns to reach other sections of the path, add the same condition for the secondary turns on P28, 6, and 5, resetting status back to 0 upon the completion of the turns, and make sure that the value status is set to 0 for the primary turns. Finally, in the cure action delivery case, add expressions that check if the collection station is S13, 10, 11, or 8 to the condition which previously only checks for S13 using the or operator, so that if the robot delivers to a collection station with any of the specified IDs, the value of status will switch to 1, and the robot will perform the secondary turns alternatively on the way back. A common issue you'll face is the robot not being able to align with the road, resulting in it going off-road, especially after turning. To counter this, we can use PID to follow the road's centerline. PID stands for Proportional Integral Derivative, which is a control algorithm widely used in robotics and automation. It's a feedback control mechanism that continuously adjusts the robot's wheel speeds to maintain its position on the line. Let's break down the components of PID. Proportional P. This component calculates the difference between the robot's actual position and the desired position on the line. It applies a correction proportional to this error, trying to bring the robot back to the line. Integral I. The integral component accumulates the errors over time. It helps eliminate any steady-state errors that might persist due to external disturbances or sensor inaccuracies. Derivative D. The derivative component predicts the future error trend based on the current rate of change. It anticipates overshooting or oscillations and applies a corrective action to smoothen the robot's movement. Since the robot's offset from the center of the path is provided, delta distance, we can use it to calculate the PID values in equation. adjusting the robot's steering by controlling the wheel speeds based on the calculated PID value to keep it centered on the line, as shown in the sample PID function named run. To utilize the run function, copy the entire sample PID function to under the curve turn to function. Looking in the function, you will notice that it accesses and uses some new global variables, and we will have to define and initialize these new variables like we did with the status variable near the top of the code for the run function to work, namely previous error PD and PID, all with the integer value of 0, and I with the integer value of 1. Now set the forward correction case to only run the run function instead. This will cause the robot to use PID to control its wheel speeds to follow the road's center line whenever traversing forward. Understanding how to debug your program is an important tool. Besides using the information panels to view the robot's sensors and program's variables values, Python users can use the print function to print out debugging information in the CoSpace robot's console in a log format. For example, if I want to record the collection stations the robot has delivered to and the robot's distance away from them when delivering the packages, so that I can confirm the order of delivery, identify issues, and adjust the speed values, I would implement the following line of code under the delivery condition to print out the station distance and station ID when the robot finishes deliveries at collection stations till the round ends. Now we will test the whole program by saving and running it. Through observing the run, some of the trigger distance values for the turns can still be adjusted. At the end of the run, the robot will have completed deliveries to all the collection stations and a log of all the stations in sequential order, according to the path with the robot's distance away from the corresponding station. When the delivery was made will be printed in the robot's console.